Okay, let's unpack this. Imagine you're deep in the LLM trenches, right? You've just trained your trusty multi-head attention model, and boom, stellar performance. But then you look at your key value cache, your KV cache, and it's just guzzling memory. Like there's no tomorrow. It's like having this super fast car that needs a fuel tank the size of a swimming pool. So what do? You try everything. Multi-query attention, MQA, group query attention, GQA, maybe even multi-head latent attention, MLA. And sure, yeah, they slash that cache, but then bam, capacity tanks. Performance takes a real hit. It's that classic AI dilemma, efficiency or power. Which one do you choose? You realize the core bottleneck, the real sticking point, those rigid low-rank limitations in the query key circuits. That's, basically how the attention mechanism processes information. You need something different, a breakthrough. So you go back to the drawing board. You design something fundamentally new, multi-matrix factorization attention, or MFA. This isn't just a tweak, it's like a whole new way of thinking about it. MFA scales attention heads and dimensions through incredibly smart factorization.
And suddenly, that 7 billion parameter model you've poured your life into, trained on 1 trillion tokens, MFA cuts its KV cache by, get this, a jaw-dropping 87.5%, from 196.6 kilobytes down to a mere 24.6 kilobytes per token. And here's a kicker. It still outperforms the traditional multi-head attention. It actually goes from 49.0% average accuracy up to 39.9%. Better performance, way less memory. But you're not done. No, you push even further, creating MFA-Key-Reuse, or MFA-KR. This genius variant reuses the key cache by cleverly re-parameterizing the value projection. Another 50% of that already tiny cache, gone. Down to just 12.3 kilobytes per token. We're talking only 6.25% of MHA's original cache. Like, almost nothing. And the performance dipped just a tiny 1%, landing at a still really impressive 48.0% average. You test its true metal right, scaling up to bigger models, even more tokens. And MFA, amazingly, it matches multi-head attention's loss curve. It proves its robust modeling capacity. And those KV savings, they actually grow with model size. It gets better as the models get bigger. You compare it to MLA, multi-head latent attention, MFA just breezes past.
It integrates seamlessly with standard stuff like ROP, rotary positional encoding. No extra hacks needed. And unlike MLA, there's no initialization fragility, none of those weird performance gaps depending on how you set it up. It just works. You check the math, the theory. The total effective rank of MFA, that's a measure of how much detailed information it can handle. It absolutely crushes the others. It gets closer to the theoretical ideal, that fully parameterizable linear attention thing, than any other variant out there. They say, but wait, cache cuts always hurt capacity. You show them the ablation studies. MFA's heads actually have a higher effective rank. They're more expressive. And it does this without blowing up the parameter count. They'd say, but it's just a tweak, right? A small optimization. Then you point to the 1 billion parameter model results. MFA hits a perplexity of 6.35 with a tiny 20 kilobytes of cache. Meanwhile, MHA needs a massive 163 kilobytes for a slightly worse perplexity of 6.41. At that point, they just go quiet, and you realize you didn't just shrink cache. You built a way to scale attention's very soul without starving its memory. A true bridge between capacity and constraint. A system that works for every large language model, every context, and honestly, every budget. That intense, almost poetic summary tells you exactly what we're diving into today. The intricate world of attention mechanisms in large language models, and this really revolutionary approach that seems to be solving one of their biggest bottlenecks.
It really is fascinating, isn't it? How this innovation, multi-matrix factorization attention, MFA, directly tackles that core challenge facing the next generation of powerful AI, which is, how do you make them both smarter and dramatically more efficient? It seems like you should have to choose. So today, we're going to unpack exactly how MFA and its variant, MFA-KR, managed to achieve these seemingly contradictory goals, how they let LLMs scale up without, breaking the bank on memory.
So let's start right at the beginning then. Why are these large language models such, memory hogs in the first place?
Yeah.
What exactly is this bottleneck we keep talking about?
Right. Well, the primary bottleneck, especially during the decoding phase, that's when an LLM is actually generating new text. Token by token is something called the key value cache memory footprint. The KV cache, think of it like the LLM's short-term working memory. Every time the model generates a new word or, a piece of text, it needs to remember all the previous words in that conversation or sequence. That's crucial for context. And these crucial memories are stored in the KV cache. The real challenge, the headache, is that this memory grows linearly.
Linearly? How so?
It grows linearly with both the number of ongoing conversations you're having with the AI, we call that the batch size, and also the length of each individual conversation, the sequence length. So as researchers like Yuan and others pointed out earlier this year, this linear growth leads to a large amount of memory occupancy and traffic. It very quickly becomes the primary bottleneck during the decoding phase. It basically limits how long your AI can remember things accurately and how many conversations it can handle at the same time before it just runs out of digital breath, so to speak.
Okay, that makes sense. So if this memory problem has been such a well-known headache, what if people tried before MFA came along? Surely they didn't just ignore it.
Oh, absolutely not. This raises an important question. What have researchers tried before? And you're right, there have been several attempts. They primarily focused on reducing the KV cache, either by sharing information across heads or by compressing those key and value memories. For instance, you mentioned multi-query attention, MQA, and grouped query attention, GQA. Both of these work by having multiple attention heads share the same key and value projections.
So instead of every head needing its own memory space.
Exactly. Instead of each head needing its own distinct set of memories, they share from a common pool. Saves memory, which is good. Then there's multi-head latent attention, MLA. This one takes a bit of a different approach. It applies what's called low-rank compression to the key and value projections, and then it only caches the latents.
Latents, like a summary.
Yeah, you can think of it like trying to summarize a long document into just a few key bullet points to save space. That's the basic idea. However, the big drawback, the catch with all these earlier methods, MQA, GQA, MLA, is that they generally fail to match MHA's performance under stringent KV cache budgets.
Ah, so the trade-off bites you.
Precisely. And why is that? Because the added constraints on key and value projections limit the capacity of the attention module. You put these restrictions on to save memory, but those same restrictions limit how much the model can actually learn and how well it can perform complex tasks. It's that core trade-off. Efficiency gain often meant a hit to modeling capacity.
That makes sense. It's like trying to pack too much into a small suitcase. You save space traveling, but maybe you have to leave some important things behind. So if we're talking about capacity, how do we actually measure that? Is there like a theoretical limit? A perfect attention mechanism?
There absolutely is, theoretically speaking. And that's where the generalized multi-head attention, or GMHA, framework comes in. It's really useful. Think of GMHA as a kind of universal blueprint for understanding all these different multi-head attention mechanisms we're discussing. It breaks them down into two main parts. There's the query key, or QK circuit, which is all about how information flows and connects between different parts of the input. And then there's the value output, or VO circuit, which decides how that selected information is then transformed and used to produce the output.
Okay, QK for connection, VO for transformation.
Yeah,
got it.
Right. And within this GMHA framework, we have what's considered the theoretical upper bound of capacity. It's called fully parameterized bilinear attention, or FPBA. If we connect this to the bigger picture, think of FPBA as the ultimate no compromise, the Ferrari of attention mechanisms. Full power, zero compromises on expressiveness.
The ideal scenario.
Exactly. It's built on three core design principles. It allows for really specific, fine-grained interactions between different pieces of information, channel-specific interactions. It doesn't force any rigid additions or combinations, no additivity constraints. And it fully utilizes all the available information without any compression shortcuts. Maximum freedom, maximum expression.
So MHA, the standard one, and these other variants.
Yeah.
They're trying to be Ferraris on a budget.
That's a great way to put it. MHA and its variants are essentially trying to approximate that FPBA power, but using clever shortcuts to stay within computational and memory budgets. Mathematically, they rely on low-rank approximations of those complex, full-power FPBA components. The genius really is in making those approximations good enough that you still get excellent practical results without needing infinite resources.
That Ferrari analogy really helps visualize it. So FPBA is the dream, MHA and the rest are the practical, clever attempts to get close. How do we then, quantify this trade-off between that ideal power and the efficiency we need?
Excellent question. And that's where two key metrics come into play. Total effective rank, or TR, and shared latent subspace dimension, SLSD.
TER and SLSD. Okay.
TR, total effective rank, is basically the product of the number of attention heads you have and how much unique detail each individual head can process its factorization rank. To put it simply, a higher T indicates a greater overall capacity for the attention model, more ability to learn and understand nuanced information.
More capacity, higher tier. Makes sense. What about SLSD?
SLSD, shared latent subspace dimension, is the dimension or size of the common workspace that all the attention heads share. Think of it as the shared memory pool. Now, a smaller SLSD reduces the KV cache size, which is fantastic for memory efficiency. That's what we want. But it can also constrain the model's overall capacity if it gets too small.
Ah, the constraint part.
Right. The critical balance, the real trick researchers are always trying to optimize, is this. The individual detail each head processes, its factorization rank, must not exceed the size of that shared workspace, the SLSD. It's like giving each chef in a kitchen a unique complex recipe with lots of ingredients that's like a high rank contributing to TR, but they still all need to fit and work efficiently within the shared kitchen space, the SLSD. You're balancing individual expressive power with the overall system's shared resources.
Okay, I think I'm following. Balancing individual head power rank with the shared space, SLSD. So this brings us back to MFA. Here's where it gets really interesting, right? Multi-matrix factorization attention, MFA, doesn't just trim the fat. It fundamentally rethinks how attention works to keep that capacity high while slashing memory. So the team asked themselves, how can we achieve this seemingly impossible balance? Their answer involved basically 3 brilliant shifts in design philosophy. First, they dramatically increased the number of attention heads and also the expressive freedom, the rank of each individual head. This gives the model more diverse viewpoints, more ways to look at the data, and it minimizes the need for heads to share information in restrictive ways. Boost the model's overall understanding.
More eyes on the problem, essentially, and each eye sees more clearly.
Exactly. Second, they got incredibly clever with how information was stored and processed. They applied aggressive, low-rank matrix factorization specifically in the QK circuit, making it extremely parameter efficient. Smart math to save space. And third, they streamlined the memory itself by utilizing a single key and value head technique. This leads to truly minimal KV cache usage. This is a game changer because MSA's specific low-rank factorization in that query key circuit, the core info processing part, allows the KV cache per token to be drastically reduced down to a dimension of just 2C. And C here is a much, much smaller number than the dimensions you typically see in traditional multi-head attention. It's about being incredibly smart and targeted with how you use that memory space.
And what's really fascinating here is seeing how these, frankly, elegant design choices translate into tangible, real-world benefits for these LLMs. First off, MFA offers a truly scalable head count. It allows developers to increase the number of attention heads, getting more diverse perspectives with minimal additional parameter overhead. So it doesn't make the model itself much bigger or harder to train. And crucially, as you said, the KV cache size remains constant regardless of how many heads you add. That is absolutely huge for scaling models up to be larger and more complex without that memory usage just ballooning out of control.
Constant cache size, regardless of heads. Wow.
It's a big deal. Second, it provides enhanced head expressiveness. Each individual attention head in MFA actually has a higher effective rank. That value C we mentioned is often greater than the YID you see in other typical approaches. This higher rank dramatically improves the expressive capacity of each individual head, allowing for more nuanced, more detailed information processing within each one.
So each head is smarter, basically.
In a way, yes. More capable. And finally, a really practical point. MFA boasts superior compatibility with positional encodings, unlike some previous methods, like MLA, which sometimes needs special handling.
Right, you mentioned the ROPE hacks.
Exactly. MFA seamlessly integrates with mainstream positional encodings, such as rotary positional encoding, ROPE. This means no weird hacks, no additional complexity are needed. It just slots into existing transformer architectures much more easily, ensuring broader applicability.
Okay, so MFA is the big breakthrough.
Yeah.
But then they went even further, right, with MFA-KR. If MFA is the breakthrough, then MFA-Key-Reuse, or MFA-KR, sounds like the hardcore memory miser.
That's a good way to describe it.
So MFA-KR pushes the limits even further. Its primary purpose seems to be just dramatically reducing that KV cache even more, right, by reusing the key cache.
Precisely. It reuses the key cache information. It does this by cleverly re-parameterizing the value projection based on the key projection during training.
It's not just copying the key to the value, though.
No, it's more subtle. It's a retuning process. There's a specific parameter, they call it alpha, which links the key and value projections. The clever trick here is that this alpha parameter is initialized as a zero vector.
Zero vector. Why?
For training stability. By starting at 0, it ensures that initially the value projection, SV, perfectly mirrors the key projection. Then, during training, the model learns how to adjust alpha just enough to capture the necessary value information while still leveraging the existing key cache.
So it starts identical and learns the difference it needs.
Exactly. And this ingenious approach means that MFA-KR effectively reduces the KV cache size by an additional 50% compared to MFA, which means, as you calculated earlier, it needs only a mind-boggling 6.25% of the original MHA cache. It's truly squeezing every last drop of efficiency out of the system.
Incredible, just 6.25%.
It really is. So, naturally, to test these bold claims, better accuracy with less cache, extreme cache reduction with minimal loss, the researchers put MFA and MFA-KR through some pretty rigorous testing. They used 7 billion parameter mixture of experts models, MOE models, which are already quite sophisticated, and they trained them on a massive data set. 1 trillion tokens.
1 trillion, that's serious training.
That's serious training. They used high-quality internal training data, a standard BPE tokenizer, RMS norm for normalization, the Xiaol activation function, and as we mentioned, rotary positional embeddings, rope-E, standard but solid setup. The key metrics for evaluation were, of course, average accuracy across a range of benchmarks, and crucially, that KV cache usage per token.
Okay, so moment of truth. What does this all mean when the rubber meets the road? How did MFA actually stack up against the standard MHA?
The results were pretty striking.
Yeah, MFA actually achieved a superior average benchmark accuracy, 49.9% compared to MHA's 49.0%, so slightly better accuracy.
While drastically cutting KV cache.
Right, by an incredible 87.5%, from 196.6 kb down to just 24.6 kb per token. That's not just about saving memory. It's like you said, it's about doing it better.
It really challenges the old assumption.
Totally. Then there's MFA-KR, the memory miser. How did that one do?
Well, MFA-KR went even further on the memory front. It reduced cache usage to an astonishing 12.3 KB per token.
That's the 93.7% reduction compared to MHA we talked about.
Exactly, a massive reduction. And it came with only a very slight accuracy trade-off, landing at 48.0%, still very respectable performance.
Which makes MFA-KR seem ideal for scenarios where memory constraints are just absolutely paramount, like maybe edge devices or situations with huge batch sizes.
Precisely. It gives you options depending on your priority. The ablation studies, which are nicely visualized in Figure 1 of the paper, they really show this trade-off landscape. MFA and MFA-KR essentially establish a new Pareto frontier for accuracy versus memory. Think of a Pareto frontier as the line showing the absolute best possible combinations you can achieve. MFA moved that line significantly outwards, clearly outperforming MLA and the baseline MHA-GQA-MQA family on this trade-off curve.
And you mentioned MFA didn't need those extra ropey hacks that MLA sometimes requires.
Right. It fits more seamlessly into existing systems. And this robustness is key for real-world deployment. MLA, surprisingly, showed this significant sensitivity to how it was initialized. It needed very specific setups to perform well.
Which isn't ideal if you just want something that works reliably.
Definitely not. MFA and MHA, on the other hand, were robust across different initializations. The paper even quantifies it. The validation perplexity gap for MLA between different initializations was quite noticeable, 6.73 versus 6.48. MFA and MHA just didn't have that problem.
And it's not just theory or big models. You highlighted the 1 billion parameter results, too.
Yes, that's important. It shows the principle holds at different scales. MFA hits a perplexity of 6.35 with only 20 kbs of cache. MHA needs that whopping 163 kb just to get a slightly worse 6.41 perplexity. So it's consistently more efficient across the board. It really isn't just a minor tweak. It feels like a fundamental improvement in efficiency.
So performance is great, cache is tiny. What about scalability? Does this advantage hold up as models get even bigger?
That's the million-dollar question, right? Or maybe billion-parameter question these days. And if we connect this back to the bigger picture, scalability is one of the most exciting aspects here. As shown in their Figure 3, MFA impressively matches multi-head attention's loss scaling behavior. As you train both types of models on more data, their performance improves at roughly the same rate. This firmly confirms MFA's strong modeling capacity. It learns just as well as MHA.
So it doesn't hit a wall early or anything?
Doesn't seem to. MFA-KR shows a very similar trend, just with that small, consistent performance gap we discussed earlier due to the extreme cache saving. But crucially, when you look at the KV cache usage per token across different model sizes, say, Going from 1B to 7B parameters, the relative savings from MFA and MFA-KR actually grow with the larger model sizes.
They save even more proportionally as models get bigger.
Exactly. This happens because MFA manages to achieve a higher total effective rank, that tier metric, compared to other methods like GQA or MQA, especially at stricter cache budgets. It gets closer to that theoretical capacity ceiling of FTBA we discussed. This means it's inherently designed for robust scalability. It's efficient and it scales well, which is absolutely vital as models continue to grow ever larger. It seems future-proof in that regard.
And did they test it with anything other than ROPE?
They did. They also checked compatibility with alibi, another type of positional embedding. And the advantages of MFA held up there too, which further confirms its broad compatibility and robustness across different architectural choices.
Okay, so MFA and MFA-KR look really promising. Did the paper mention any other related work, other ways people are trying to tackle this memory beast?
Yes, they briefly touched upon a few other related areas. There's research into things like cross-layer attention, CLA, and multi-layer key value, MLKV. These try to share the KV cache between different layers of the model, not just within a single layer's attention mechanism.
Sharing across layers.
Yeah.
Interesting. Does that help with the traffic bottleneck?
Well, that's the caveat they noted. While these methods might reduce the total memory storage needed, they don't necessarily reduce the underlying memory traffic during the core attention computation itself. So the latency benefits might be less direct compared to reducing the per-token cache size like MFA does.
Gotcha. Any other approaches mentioned?
They also briefly acknowledged the existence of entirely different approaches that move away from traditional softmax attention. Things like state space models, Mamba is a well-known example, or various linear attention mechanisms. These often have the advantage of a constant cache state size, meaning the memory doesn't go linearly with sequence length at all.
Constant cache. That sounds amazing for long sequences.
It is, but often comes with its own set of trade-offs in terms of modeling capabilities or training dynamics. The paper wisely suggests that these alternative attention mechanisms could potentially be combined with MFA's techniques in the future, perhaps leveraging MFA's efficient head structure within a linear attention framework. That's an interesting avenue for future work, especially for extremely long context scenarios.
Okay, combining the best of both worlds, potentially. Now, no research is perfect. Did the authors talk about the limitations of their own study? What's still left to figure out?
Yes, and it's always good science when authors are upfront about limitations. They acknowledge several points. First, their study didn't directly evaluate the full system-level implications of this KV cache reduction. Things like the exact impact on end-to-end inference latency or throughput for very large models processing very long contexts in real-world deployment scenarios. That requires more engineering and system-level testing.
So the theory and component-level tests look great, but the full pipeline impact needs more study.
Precisely. Also, as we just touched on, the integration of MFA with other architectural innovations like that cross-layer attention or linear attention hasn't yet been explored. Combining these could potentially unlock even further optimizations. They also noted that performance validation at scales even larger than 7 billion parameters hasn't been conducted yet. While the scaling trends look promising, confirming them on, say, 70B or larger models would be important future work.
Makes sense.
Mm.
Keep pushing the scale.
Yeah.
Anything else?
And finally, a small but interesting point. The underlying reasons for why MLA showed that surprising sensitivity to initialization. They're still unknown. It works. But MFA seems more robust, and understanding why MLA is fragile could offer further insights into attention mechanisms generally. That remains an open question.
Okay, so quite a bit learned, but still more to explore. Let's try and wrap this up. What does this all mean for you listening in? We've seen how this multi-matrix factorization attention, MFA, and its super efficient sibling, MFA-KR, have really cracked the code, it seems. They're giving us large language models that are not just powerful, but also incredibly memory efficient. They found that sweet spot, that balance point, allowing for enhanced capacity, better performance even, without starving the system for memory. Just to recap the numbers, because they're pretty staggering, MFA delivers 87.5% less KV cache with better accuracy than the standard MHA, and MFA-KR pushes that reduction to a staggering 93.7% with only a tiny, tiny performance dip. It's like having that supercar that somehow sips fuel.
And this raises, I think, an important question for you, the learner. Why should you care about all these technical details, the TER and SLSD and factorization? Well, because this research directly impacts the future of the AI you interact with, probably every day. Faster, cheaper, more accessible, and more capable, large language models. That's the promise here. It means everything from a smoother, faster chatbot experience on your phone to enabling breakthroughs in scientific research that require processing huge amounts of data to unlocking entirely new creative applications we haven't even thought of yet. This isn't just some incremental improvement for academics. It's a fundamental step towards making advanced AI more pervasive, more practical. It moves us closer to a world where these powerful models can run on more diverse hardware, maybe even locally on your devices, and handle ever longer, more complex interactions without hitting that memory wall.
Yeah, it really lowers the barrier to entry in some ways. Okay, final thought then. They always say cache cuts hurt capacity. That's been the mantra. Sacrifice performance for efficiency. But what if we've just seen the tip of the iceberg here? What if this approach, this really smart factorization, this way of thinking about attention, heads differently? What if it opens the door to fundamentally different LLM architectures we haven't even conceived of yet? Models that are not just more efficient, but maybe inherently more powerful because of their design, because they've broken free from these old memory constraints. What are the truly mind-bending possibilities when we're no longer fundamentally limited by memory in the same way? What comes next?